From the Oregon State University Extension Service, this is Pollination, a podcast that tells the stories of researchers, land managers, and concerned citizens making bold strides to improve the health of pollinators. I'm your host, Dr. Adoni Melathopoulos, Assistant Professor in Pollinator Health in the Department of Horticulture.
I always love going to pesticide recertification talks. As many of you know, I give a talk on how to understand the pesticide label to pesticide applicators. And, in those talks, I realized that there's a whole range of tools that applicators rely on to ensure that the pesticide is used efficiently and effectively. And one area that I'm really fascinated with is these products that are known as adjuvant. They're applied in the tank with the pesticide, and they may be used to make sure that the pesticide sticks to the plant or reduces its drift to adjoining areas. There's a whole host of these adjuvants. Now, until now, the effect of these adjuvants in combination with pesticides on bees has been not really well characterized, and that's where today's guest comes in. Brandon Shannon is a master's researcher in the Environmental Sciences program at The Ohio State University. He's in Dr. Reed Johnson's lab, and he's focusing on the toxicity of these pesticide adjuvant tank mixtures, what a grower might commonly use to honeybees. So in this episode, we're going to hear about what these adjuvants are, and we're going to hear about his great research that's opening this whole area of how these products, which products may be problematic, which may not be, and some of the trends he's viewing. He also has some great recommendations if you are a pesticide applicator or a beekeeper on how to maybe mitigate this, the risk of adjuvants, especially now when this field is just emerging and we don't have a lot of information. So without further ado, let's head to the other OSU this week with Brandon Shannon. Well, I am so excited to host you today on Pollination. Welcome.
Thank you. I'm excited to be here.
So, Brandon, let's begin. We're going to have this big conversation today about these things called adjuvants. What is an adjuvant? Why do pesticide applicators use them? And, these are used in conjunction with pesticides. So it raises the question, how are they regulated?
So an adjuvant is any product that is added to a pesticide mixture. These aren't necessarily included with the pesticide, but are separate products that are added to pesticides. And what they do is they can have many different properties. The ones we see most commonly are surfactants, penetrants, and stickers, which will allow the pesticide to stick onto the leaf better and spread out that pesticide onto the leaf to make it more effective. But there can be many other different reasons they're used, such as pH balance, drift reduction, or really any other property that you would want to have in your pesticide tank mixture, even to help mixing better when you're adding multiple pesticides together.
I saw this recently. It was at a pesticide talk, and somebody was working with wettable powders and pointing out with, the addition of an adjuvant, it wouldn't cake up. And in some ways it had this beneficial purpose because then you would get the right rate rather than a clump of, high. It would just kind of spread it out a little bit better.
Right. And they could be really beneficial to a lot of pesticide applicators because of reasons like that. Part of the problems with adjuvants is they are not really regulated by EPA very much. Most of the ingredients that go into these adjuvants are called principal functioning agents instead of being called active ingredients. They're called principal functioning agents because they don't have any pesticidal properties, but they're considered inert ingredients by EPA. And that doesn't mean that they don't do anything, that they're inert necessarily, but that's their definition of something that doesn't have pesticidal properties that will bypass a lot of this regulatory testing that's required of pesticide active ingredients.
Okay, so there are these key ingredients that make it spread or stick or not drift, but these ingredients are don't go through the same risk assessment process that a pesticide would.
Yeah, exactly. And often multiple adjuvants are added to the same tank mixture. For example, in California, where almonds are grown. We can look at the CalPIP database to show us all of the pesticide usage through California. There are just over 1 million acres of almonds in California, and there are about 1 million acres of fungicides applied. So between the blooming period, so about one fungicide application for every acre. But in almond or in adjuvants, we see that it's about four times that. So you have about 4 adjuvants applied per acre of almonds. And so what these pesticide applicators are doing is adding an adjuvant for every property that they want to improve. So they'll add an adjuvant to balance the pH. They'll add another adjuvant to stick better, another adjuvant to penetrate the leaf better, another adjuvant to reduce drift. And it's just making these pesticide cocktails, basically, where we don't really know what the interactions are within them.
That's fascinating. It makes me, are we talking, there must be lots of adjuvants then, because if they've got all of these specific niche, purposes, there must be, we're not just talking about like 4 products. There must be a whole family of them.
Right. Looking at the CalPIP database, and now this is only California for use in almonds, there are hundreds and hundreds of adjuvants that are being used. And that really limits our research because we can't test everything. It's impossible. And so we were able to test 12 adjuvants, and the adjuvants we tested affect about 25% of almond orchards of the total adjuvant application. But yeah, there's no way to test these hundreds and hundreds of adjuvants, at least in one single lab like we're doing. You'd need a much bigger operation to do something like that.
Well, let's transition to your research in just a second, but I just wanted to clarify CalPIP. What's CalPIP? So
CalPIP is the California Pesticide Information Portal, and it is a database in California that basically registers all of the pesticide use, in this case for almonds, and it's really useful for us, so we can see what these pesticide applicators are actually using, and beekeepers may be interested if they are in California or take their bees to California to see what pesticides are around them, and they can use this database as well.
Okay, so it's kind of like but it also at the same time this, and I understand that this is pretty unique to California, but it also captures the adjuvant data. Is that correct?
That's correct. Yeah, it has all of the insecticides, fungicides, and adjuvants as well.
Okay, sorry for the sidetrack. Thanks for the clarification. So you became really interested in adjuvants, and it's been an area that I've been hearing about both from applicators, but also researchers about the potential impacts of adjuvants. You were interested in the specific question of tank mixing adjuvants as they are you described in California with a fungicide or with an insecticide, and asking the simple question, are they toxic to bees? Can you describe how you approach this question? What's your kind of like methodology for answering this huge ball of wax?
Yeah, so we hypothesized that adjuvants. Well, to start off, the reason we asked this question is because a lot of beekeepers that are taking their bees to California for almond pollination, it's about 85% of the nation's colonies are going to California, which is about 2.1 million colonies in 2021. A lot of them are reporting colony losses, and about 1 in 5 beekeepers report that they experience colony losses that they believe are due to pesticide death in their bees. And so the pesticides that are used during bloom are tested, and they're determined to be safe for bees. So we're saying, what is it in these pesticide mixtures that's causing this toxicity? So we decided to test these adjuvants. So first we hypothesized that they would be toxic both alone and in the combinations with the tank mixes. And now the combinations are really important because adjuvants are never applied on their own because they don't have their own pesticidal properties. They're always applied in combination with these pesticides. So what we did is we used what's called a Potter spray tower, which simulates an application of a pesticide tank mix, and it basically takes the same application rate that is being applied to the field level, and it applies it onto a petri dish of bees. Now, these bees we collect from what's called a frame of brood, where you have pupating bees, and then when the bees will emerge from their cells, we will put them in a cage and age them to 3 days old so that all of the bees are uniform. This is the same methods that EPA uses to do their toxicity testing on bees. And we tested the toxicity after 48 hours after spraying with this simulated spray application onto these bees at different concentrations. It was also important that the concentrations that we used are based on not percent concentration or grams per liter concentration, but instead it's based on the application rate. So we wanted to keep it as application focused as possible. So we would try to determine mortality using applications at 1 times the application rate, at 3 times the application rate, at 10 times the application rate, and so on. So that kept it as application focused as possible. So you can see kind of the range of where bees will actually be exposed to these adjuvants.
So these are kind of worst case scenarios. This is kind of like the 1 times would be if the bees found themselves under the spray nozzle, and this is what they get. And so this is kind of allowing you to really pull apart by kind of taking the dose up to just see, look for these effects. I imagine that's the kind of rationale for going upwards.
Yeah, exactly. Because what we really want to do is create a dose response curve. And so at each concentration, what is the mortality? And then at what concentration do you kill 50% of bees, which is known as your LC50? This is a measure that's frequently used in toxicology to compare different toxins, such as pesticides or the like. And so we had to go above the 1 times application rate for this reason. And it was really only to see, how toxic, how high do you have to go to see toxicity in our lab study.
Okay, great. Well, I want to give this as a teaser. We're going to take a quick break now, and we're going to come back, and you're going to reveal all, because you've really been able to kind of, with this methodology, go through a lot of combinations and reveal a lot of information. So let's take a quick break. We'll be right back. Okay, great. That was a good break. And there was one thing that you wanted to mention, Brandon, about your methodology. Why don't you, we were talking about the rates that you selected, and that when you get a pesticide, oftentimes it doesn't give you one rate, it gives you a high and a low. So tell us a bit about the selection that you used for the experiment.
Yeah, adjuvants are very similar in that they give you a range of the application rate. When I'm talking about 1 times the application rate, I'm talking about the maximum application rate. So the application rate will be, from 1 to 4 pints per 100 gallons concentration. And so we'll be using that 4 pints, not that 1 pint. Now, what we see looking at the CalPIP database, the California Pesticide Information Portal, we see that most applicators are not really applying at that maximum application rate. They're applying closer to that 80% range is kind of the median range that's being used and the most common.
Fascinating.
But what we wanted to do is find that worst case scenario that legally bees could be exposed to based on the label.
Okay, that's excellent. Thanks for the clarification. And I know everybody is dying to know, what did you find? Is a mixture of adjuvant and insecticide or fungicide more toxic than its parts?
Yeah, so it was really interesting. So the adjuvants alone we tested, and we found that 4 of the adjuvants had toxicity, an LC50 of about 10 times the application rate. Now, safety factors are usually around a factor of 10 for when that lower limit of effect starts showing up. So by definition, those would be toxic at near application rates. And then we found 3 others that were toxic at a kind of a median toxicity of less than 30 times the application rate. Now, you might say bees will never be exposed to this in typical field applications, but often in aerial applications, when they're using a drone or a plane to fly over and spray their crops, these are often recommended to be sprayed at 100 times the concentration of what they are in ground applications. So it is possible that they could be exposed at those high concentrations. And then in combination with insecticides.
Let me get this straight. So these adjuvants are toxic, but the rates are, they have to be higher. And there may be some field contexts where they're at that high level, but alone, they have some toxicity at above the rates that they're being used.
Yeah, exactly. And that is just applied by themselves, but we never see adjuvants applied by themselves. They're always applied with a pesticide. So we also tested the combination toxicity, and we found for 3 of our adjuvants, we showed increased toxicity when combined with one single pesticide. So this is one adjuvant with one single pesticide. And what it did is it basically cut that LC50 in half, or almost doubled that toxicity. And that is just one single pesticide. We don't know what 2 pesticides would do, what 3 pesticides would do, or what adding extra adjuvants would do. And it's really impossible to test because you have an infinite number of combinations with adjuvants and pesticides together. So we were kind of limited in testing only one adjuvant and one pesticide. We also saw that some had antagonism, we call it, which is where when the pesticide is added to the adjuvant, you actually see decreased toxicity. This was not as common, but it was still interesting to see, and we're not really sure why the antagonism is happening. But it was just interesting to note, and it just kind of shows the unpredictability that you can have in these pesticide tank mix cocktails when you are adding many things all at once into one tank mixture.
So just go through this again as well. So you tested a number of pesticides, right, with adjuvants, and it was just give us a sense of how did they all, you said one of them experienced this paradoxical, antagonism, where I think that's the word you used.
Yeah. So the trend was not in the pesticides. Most of the pesticides behaved similarly within the same adjuvant. So when we tested one adjuvant, if it became more toxic with one pesticide, it typically became more toxic with all the pesticides that we tested. And now this was 4 different fungicides and 2 different insecticides that are commonly used in almond orchards. And I said before, but I'll repeat it again, that these pesticides show no toxicity on their own to honeybees in EPA testing and in our testing as well. And so they have no bee hazard labeling, and they're used at times when almonds are in bloom and often when bees are active.
Okay, so these are, sorry, I actually missed that part. So these are fungicides in general don't have any, labeling on them, hazards, but these
specific fungicides,
these ones don't, for sure. Mm-hmm. And then the insecticides all are ones that have an LD50 or have been assessed, their risk has been assessed, and they're not risked as being at the rates that they're being prescribed hazardous to bees. But then when they're combined with the adjuvant, then suddenly a product that an applicator reading the label thinks this is a product that can be applied even at full bloom, suddenly, it's becoming toxic.
Right, exactly. And we think that it's not necessarily the pesticides becoming toxic, but instead the adjuvants becoming toxic. Now, we haven't done anything to prove that yet. That's just kind of my hypothesis and opinion on that. And the reason we came to that conclusion is because these adjuvants are showing toxicity at near application rates, and the adjuvants are increasing or decreasing in toxicity, the same for every pesticide. And the pesticides are not showing any toxicity at the rates we tested, which is up to 100 times the application rate. I mean, that's outlandish concentrations.
So your hunch is based on the fact that if it was a synergism. It would, for one pesticide, it would be high, another one, it would be low. But the fact that it's right across the board makes you suspect that there's something about mixing it with some other product that makes the interesting hypothesis.
Yeah, and it's also, we don't know for sure if it's the pesticide active ingredient or the pesticide also has its own inert ingredients present in it. It has the active ingredient plus its own kind of almost adjuvant in of itself that are added to the pesticide active ingredient to make it, dissolve better or penetrate the leaf better. And so we don't know if the adjuvant is interacting with the pesticide active ingredient or if the adjuvant is interacting with the inert ingredients that are present in the pesticide formulation.
All right, because the pesticide is not merely the active ingredient. There's other things that are forming. It could be, it's hard to sort of parse out causation, but there's clearly, you can see these patterns, and the patterns are some adjuvants don't seem to have an effect. Some seem to have an effect, but the effect is right across vastly different pesticide chemistries. And it's sort of like, which sort of opens up this, but the reason that's happening, what's the mechanism, is now, I guess, for yourself or others to explore and discover.
Exactly. Yeah. And, we got as many questions on this research topic as we got answers. So it's going to be really interesting to see what we find out next. So
I love that. Actually, I think good research is like that. I always think I can sense a really carefully done project when the results don't meet your expectations, and it generates so many more questions. But it does come back to the field now. Now, research like this comes out, and pesticide applicators who want to do a good job are now confronted with this Pandora's box of knowing that sometimes it's a problem, sometimes it's not a problem. What are they to do? It sounds like a lot more of this kind of grinding through spraying combinations is needed to be able to see if there's any predictable pattern between related adjuvants or what's going on. What's your advice? When you give this, I imagine you talk to pesticide applicators, and what do you tell them?
Yeah, so I'll start with, in 2017, the Almond Board of California, who advises a lot of these almond farmers and growers that are applying the pesticides, they advised against the use of adjuvants entirely. And so they said, don't use adjuvants at all. Now, I understand that some pesticide applicators feel the need to use adjuvants, and they're really limited on the rates of pesticide they're allowed to use, and they really want to protect their crop, and that makes sense. So what I would say would be a good, meeting in the middle would be, instead of using these adjuvants at the maximum application rate or even the 80% application rate that is typically used, use it at the lowest concentration that's listed on the label. We say in toxicology often the dose makes the poison. So the more adjuvant you're adding into this tank mixture, the more possibility for toxicity that you would see. So I would say use lower application rates when possible, and maybe limit the number of adjuvants or number of constituents in your pesticide tank mixture cocktail that you're adding in. And then secondly, I would say it's probably best to apply in the evenings when bees and most other pollinators are not active. In almonds, it's almost entirely honeybees because it's so early in the season, but this could apply for other crops as well when other pollinators are also present. And so applying in the evenings would prevent this kind of worst case scenario of a bee being directly sprayed with a pesticide application. And instead, only the residues would be left over, which would be at a lower concentration and are typically not as toxic as a direct spray would be.
And I imagine some of them, I've seen some of these adjuvants, it's just foamy, bubbly stuff. And by the next morning, it's just like it dries down, and it's sort of maybe not as, it's not in the modality where who knows, I guess, but this is the thing in light of just some emerging research and just taking caution, just spraying in the evenings and using those lower rates of the adjuvants could be two good mitigation strategies. And I imagine the other one is that the highest risk of doing this is when it's a bee attractive plant in bloom, that once it's out of bloom, that perhaps, the bees won't be in the crop as much as.
Yeah, exactly. The problem with almonds is that they are blooming at the same time when that fungus that is being targeted by the pesticide is really taking off. So they really need to spray during bloom in order to protect their crop. But so if you were going to, it would be best to not spray during bloom. But if you had to spray during bloom, it's best to do it in the evenings.
Well, Brandon, your research has opened many cans of worms. What do you think are the kind of pressing? I didn't ask this. I sent some questions in advance, but I'm really curious. When you're right in the thick of it and probably analyzing data and doing a lot of writing, and you're thinking deeply about this problem, what do you think the next steps are? What is the kind of research that needs to be done now to kind of provide applicators and beekeepers with clear directions on what to do?
Yeah, so we've kind of shifted in a couple different directions. The one is we've kind of shifted away from testing these formulated adjuvants because, like I said, there's hundreds of them and they keep producing more. So we're never gonna get that never-ending goose chase and never test them all. So what we're instead doing is testing the principal functioning agents that are the ingredients that are making the adjuvants act the way they're intended to. And so a lot of these principal functioning agents are used in many different adjuvants, as well as in pesticides as well. For example, the alcohol ethoxylates or the organosilicone surfactants. A lot of people have been doing studies on those particular chemical groups of principal functioning agent. And in determining toxicities of these specific compounds, we can make better recommendations to these adjuvant and pesticide manufacturers to kind of say, this is the safe thing to put in your product. And if you don't put this in or if you put the safe thing and not the dangerous thing in your product, you can market it as safer to pollinators, and it will really benefit everyone. The second thing that we're trying to do is forming a risk communication strategy to kind of determine where pesticide applicators are kind of have a knowledge gap with adjuvants, with this new adjuvant research that's been done, and where is the toxicity testing needed, and how can we better inform these pesticide applicators to make safer pesticide tank mix choices for our bees and other pollinators.
Those sound like both really fundamental, kind of like getting down to sort of what those principal functioning agents.
Yeah, that's right.
Yeah. How they're related and what's going on, to very practical work in terms of like, if you did kind of up with patterns, how do you, because pesticide applicators, there's so many licenses, there's it ranges from agriculture to forestry. It's a big group of people, and just figuring out how to communicate this to them, or the extent that they're aware of these issues. I think those are great two suggestions for future research. It's very exciting.
Yeah, thank you.
Okay, well, let's take a quick break. We have these questions that we ask our guests, so we'll be right back in just a second. Okay, we are back. So, Brandon, do you have a book recommendation for our listeners?
So yeah, my book recommendation is the same that every beekeeper will give you if you ask them, and that's Honeybee Democracy by Tom Seeley. I read that book a few years ago when I first got into beekeeping, and it was just really interesting to see how, it's not the queen bee who makes the decisions in the hive, it's the worker bees that make the decisions through pheromones, and the queen bee responds. And it also makes a lot of connections between how we as humans can take the decision-making strategies that honeybees use to make better decisions ourselves. And so I thought that was really interesting.
It does remind me, it's a very well recommended book on this podcast, but we had a podcast on the 18th century book, Fable of the Bees. And we had a historian on the podcast, and he pointed out that in Shakespeare, it's the monarch is at the center of, it's mirroring the monarchy of, European kingdoms. And that's what people always thought. They thought, oh, the queen, she's royalty, she must run the place. And so this book kind of brings the wealth of research that Tom has been doing on over the decades, and kind of like tipping that perception over. It's great.
Yeah.
Well, the next question we have is, do you have a go-to tool for the work that you do?
So yeah, I thought about this one for a while when you first brought it up to me, and I think my go-to tool would be the Potter spray tower. A lot of toxicology assessments in honeybees are done with micro applicators, which is when you take just a little droplet of pesticide and put it on the back of the thorax of a honeybee.
Like a little syringe with a fine needle. You're just putting like this tiniest drop on a bee's body.
Exactly. And I think we should kind of move away from that personally, because it's not necessarily indicative of what is happening in fields. I think simulating a spray application using a Potter spray tower is a much more application focused toxicology study, which I think a lot of times we really need to try to make science more application focused and less laboratory focused. And another positive is it also lets you test thousands and thousands of bees in a summer. When a micro applicator, you can only test one at a time. At a Potter spray tower, you test 20 at a time, so you can really expand your testing parameters.
Describe what this looks like. What is a Potter spray tower look like?
Okay, so it's got it's about 3 feet tall. It has at the top a little test tube that you would put your pesticide tank mix in, and then it's got a little straw that sucks out of that test tube and then sprays it out of a nozzle, and sprays it as an aerosol down this vertical cylindrical column. And then at the bottom of that vertical cylindrical column, which is about 3 feet tall, you have the spraying plate, which is just a flat plate, and you'll have a petri dish with bees on it. The bees will be knocked out with carbon dioxide, but you could do this with any other kind of insect or small organism you wanted to.
Okay, so they're going to get this fine. So it's a kind of simulating what might come out of a sprayer nozzle, and it's the other advantage is you can like go through a lot. You can dose a lot of more bees and get that replication up. Where if you're sitting there with your little syringe, you would be there forever.
Yeah, exactly. The one disadvantage is with the syringe, you know exactly the dosage each bee is getting. And with the Potter spray tower, you can only average the doses that the bees are getting. So it's not quite as scientifically sound, but I think the trade-off of being more application focused is worthwhile.
Wonderful. The last question I have for you is, do you have a favorite pollinator, and tell us why?
So I'll give you 2 favorite pollinators. Of course, the first one is the honeybee, because I work with honeybees. Honeybees are what got me into this research. And, the first time I went beekeeping, I just fell in love with, how the colony operated, just watching the bees crawl around. But I'll say
and just before you go on to your second one, and this is a good segue just to mention Reed Johnson's lab, the Johnson lab at Ohio State University, has an apiary, and it's a big beekeeping state. And you're in, the hallowed grounds of Dedant, and so tell us a little bit about the lab.
Okay, yeah. So we have 2 campuses. We have the Columbus campus, which is Maine, Ohio State, and then we have the Worcester campus, which is our agricultural campus where I'm located. And we have apiaries, that's bee yards at both campuses, and probably at peak summer manage about 40 colonies each per campus. Wow. And so a lot of these colonies die because we're taking bees out, and we're very mean to them because we're doing research with them. It's kind of unfortunate. But yeah, that's what typically happens. We have had observation hives in the past for studies that study waggle dances and things like that as well, which are really fun to watch. If anyone wants to look up a YouTube video waggle dances.
But this is great. Through your master's program, and in addition to becoming like a top-notch toxicologist, you also are learning beekeeping.
Exactly, yeah. And I'm the teaching assistant for the beekeeping class this semester as well, which is really fun to teach. So,
okay. Thank you so much. Sorry, thanks for indulging me in a sidetrack, but you said you had 2 bees.
Yeah, so my second favorite one is the alfalfa leafcutter bee. I don't think I've ever seen this one in person in action, but just watching YouTube videos of this bee they're just so cute, the way they cut little pieces off of leaves to take back to their little homes and cap their brood that way. Just watching them fly with little pieces of leaf, just fascinating to me.
Well, and I will redirect listeners, if you're interested in knowing more about alfalfa leaf cutting bees, we do have both Dr. Jim Kane, who's retired from USDA, and we have that wonderful podcast. Oh, it's slipping my mind. But we have one of the biggest leaf cutter bee producers in Southern Alberta, who's been working with them forever. So I agree with you. They're a fascinating bee, and just the culture of them, the way in which people are able to have figured out how to manage them, it's just remarkable.
Mm-hmm. Yeah, I agree.
Thank you so much for taking the time to talk with us, and good luck with your research. We're really excited to hear more results.
Yeah, thank you so much for having me on. It was really great to share our research with everyone.
Thank you so much for listening. The show is produced by Quinn Sin and Neal, who's a student here at OSU in the New Media Communications program, and the show wouldn't even be possible without the support of the Oregon Legislature, the Foundation for Food and Agricultural Research, and Western SARE. Show notes with links mentioned on each episode are available on the website, which is at pollination.podcast.oregonstate.edu. I also love hearing from you, and there's several ways to connect with me. The first one is you can visit the website and leave an episode-specific comment. You can suggest a future guest or topic, or ask a question that could be featured in a future episode. But you can do the same things on Twitter, Instagram, or Facebook by visiting the Oregon Bee Project. Thanks so much for listening, and see you next week.